Okay, starting on Unit 2 now, arc length. Number 3 asks you to show that your answer agrees with the formula that you get with the distance formula. So I went ahead and calculated it using the distance formula. Now I'm going to look at y equals 2x. I usually like to go ahead and write down y primed. So y primed is equal to 2. So length is equal to the integral as x goes from 0 to 1, square root of 1 plus y primed squared, integral from 0 to 1, square root of 5 dx. Yay, I get the exact same answer. Find the surface area formed by revolving the graph of y equals x cubed on the interval from 0 to 1 about the x-axis. Now, I usually like to sketch myself a little picture so I can visualize what's going on. Luckily, it's pretty easy to sketch a little graph of x cubed from 0 to 1, looks something like that. And we are revolving it around the x-axis, so it's going to look kind of like a trumpet. And let's see. First thing I want to do is write down y equals x cubed. So y primed is equal to 3x squared. I want to integrate with respect to x's. And remember, with surface area, you have choices. You can do it with respect to x or with respect to y, whether you're revolving around the x or the y. Now, I just wrote down the generic way that I memorize the surface area formula: 2 pi times the radius times the arc length. Arc length being square root of 1 plus a derivative squared. I want to integrate with respect to x's, so I'm going to go from 0 to 1, 2 pi. Now, with respect to x, my radius is this distance from the x-axis to my curve, which would be the y-coordinate. So if for x in terms of y, my radius, y in terms of x, my radius is x cubed, and then I have the square root of 1 plus 3x squared. I would not expect you to integrate that by hand, even though you really could, because when you square that, you're going to get 9x to the 4th power. You could use substitute it. I'm going to cheat and peek over here at the key and see what the answer. Again, I would have just plugged it in the calculator. If you were asked to do it by hand, it would not be unreasonable because it's a straightforward use substitution problem. If you want to see it worked out, you can look at the key. Let's look at number 5. We have a cylindrical water tank 12 feet high with a radius of 8 feet is buried so that the top of the tank is 3 feet below ground level. How much work is done in pumping a full tank of water up to ground level? So I'm going to put the bottom of my tank, the center of the bottom of my tank at the origin. And there's my tank. The height of the tank is 12 feet. So this is the height of the tank, 12 feet. It is another 3 feet to ground level. And remember, from the side, a cylinder just looks like a rectangle. From above, the cylinder looks like a circle, and this cylinder happens to have radius of 8 feet. So this point right here is 8 feet. But the area of looking down at the cylinder would be pi times r squared, which is 64, not 16. Pi r squared. Work is equal to the integral from the bottom of the tank to the top of the tank, so 0 to 12. The density of the fluid, which I'll check, make sure, yeah, 62.4. I'll give it to you on test day. You don't have to have it memorized. 62.4 for water measured in foot-pounds. And area, which is 64 pi, times distance. How far is each slice of water going to have to travel? Well, it has to travel all the way up above ground, so 15 minus y dy. So rho times g, all combined in one handy-dandy unit, area, distance. Easy to integrate, but I would still let you plug it into your calculator and get 1,345,996.56, and don't forget your units, foot-pounds. Okay, let's do another one. Still looking at Unit 2 stuff. Number 6, we have a cylindrical gas tank is placed so that the axis of the cylinder is horizontal. If the tank is half full, determine the force on a circular end of the tank. Assume the diameter is 3 feet and gasoline has a density of 50 pounds per cubic foot. Always draw a picture. I'm going to put the center of my tank on the origin, the center of the bottom of my tank on the origin. You don't have to. You could have put your tank so that the center of the tank was on the origin, like I said originally, even though I drew it with the bottom on the origin. It's half full, and the diameter is equal to 3, which means radius is 1.5. So here's 0 to 1.5. That means the center of my circle is at the point 0, 1.5. So it's x squared plus y minus 1.5 squared is equal to 1.5 squared is the formula for that circle. I want to isolate x, so x is equal to the square root of 1.5 squared minus y minus 1.5 squared. Force is going to be equal to the integral from the bottom of the water to, or liquid, fluid, to the top of the fluid. So 0 to 1.5 density, and that is given to us as 50. The width of a slice, so the width goes from one side of this tank to the other. The distance from the y-axis to the right side of the tank, y-axis to the right side of the tank, is your x-coordinate, the square root here. The distance to the other side is exactly the same. So this distance here is 2 times the square root of 1.5 squared minus y minus 1.5 squared. And then you have distance, which is 1.5 minus 1 from the top to the bottom. So this is width. This is rho times g. And this is distance. So just your generic help you to remember the formula for that. And let's look over here. I get 112.5 pounds. Okay, we have a spring problem. A spring whose natural length is 10 centimeters is stretched 15 centimeters by a force of 30 newtons. Find the work done in stretching it 7 centimeters beyond its natural length. Give that one a try. We'll meet back and compare. Some of the easier problems were the spring problems, I think. Remember that Hooke's law tells us that the force is equal to the spring constant times x. So since the force was equal to 30, we knew x was 0.05. Remember, newtons or joules and newtons work with meters. You were given a number in centimeters, so we had to convert. So k was equal to 600, so my force function was 600 times x. Easy peasy, lemon squeezy. Okay, number 8. We have a dam in the shape of an isosceles trapezoid, which is 200 feet across the top, 100 feet at the bottom, and 75 feet high. We want to find the fluid force if density is 62.4 feet per cubic foot. Draw the picture. Hardest part is drawing the picture. Okay, if that's an isosceles trapezoid, then the engineer is really in trouble because I didn't draw a very good picture, but I labeled it, so we know what it's supposed to be. This is the point 50, 0, because it's 100 feet wide at the bottom. This is the point 175 because it's 75 feet tall, and it's 100 feet across, or 200 feet across the entire top. I went ahead and labeled my little similar triangle, even though I didn't label it very well. If this is y, then this is x minus 50. Because x would be all the way over to the side, but it starts here at 50 for the triangle. And that has to be a similar triangle to one whose height is 75 and whose width is equal to 50. So y over x minus 50 has to be equal to 75 over 50. And I need to have a function with y's in it. So 50y equals 75 times x minus 50. And I'm going to do some arithmetic, and we'll write a function for the equation of this line right over here. Okay, I decided to divide both sides by 25 and make my numbers smaller. And then I just divided both sides by 3, isolated the x. If you don't like using the similar triangles method, you prefer finding the slope of the line that connects the 2 points and then plugging in one of the points to get the equation of the line, the key shows you how to do it that way. I don't care how you do it. I do know that the engineering department likes you to be comfortable with similar triangles, so if that is your goal, try to become comfortable with them. Not necessarily on exam day. On exam day, do it the way that works best for you. So, we're trying to find the force density. So force is going to be equal to the integral from the bottom to the top of the water, and it is full. It's a dam, so the water is pressing against the entire edge. So 0 to 75. Density is given to me, 62.4. The width of the trapezoid. So the distance from the y-axis to the right-hand side of the trapezoid is 2/3 of y plus 50. The distance from the y-axis to the left-hand side of the trapezoid is 2/3 of y plus 50. So width is 2 times 2/3 of y plus 50. So far we have density, we have width, now we need distance, and distance is 75 minus y. These numbers will often be the same. And plug all that stuff in, you get 23,437,500 pounds. Okay, we have one more unit 2 problem, and that is the volume of a solid of revolution. I promise you're going to see a volume of a solid of revolution problem, because we learned different ways of doing it. There are lots of different scenarios going around the x-axis, the y-axis, a line that's not an axis. So you will see one of these. Let's look at number 9. Volume of the region obtained by rotating the area between the 2 curves about the line y equals -3. Draw your picture. Okay, so this would be a reasonable graph that I would expect you to be able to draw on your own on test day. Simple, generic parabola shifted up 2 units and shifted up 4 units and flipped upside down. Easy to figure out where they cross. Now I'm going to draw in one of my slices. I'm going around something that's parallel to the x-axis. So my slices here are perpendicular, which means I'm going to use washers, perpendicular washers. If my slice were parallel, I would do a shell. So my volume is going to be equal to the integral from one end to the other. So one end of my region is at -1 to +1. I need the outside radius squared minus the inside radius squared. Pi times the outside minus the inside. So the outside radius squared is the upside down parabola minus -3. So I just wrote +3 instead of minus -3. minus the inside radius squared. And the inside radius squared is the distance from x squared plus 2 to y equals -3. So x squared plus 2 plus 3 squared dx. Okay. That is something I would allow you to plug in your calculator, even though it would not be that hard to do by hand. And let's see. My answer, I get 32 pi. Going to show you how to do this using shells instead of disks, but this one is not a good one to do that way. So if you want some practice with shells, go back and find some more practice problems. We'll move on to Unit 3 stuff in the next video.